Lastly, we will discuss the acid-base behavior of the oxides themselves through the neutralization reactions between the oxides and acids or alkalis. The oxides are classified as basic oxide, acidic oxide, and amphoteric oxide based on their acid-base properties. In general, metal oxides or ionic oxides are basic oxides. They act as base when react with acids to give salt and water, and there is no reaction between basic oxides and alkalis. Non-metal oxides or covalent oxides are acidic oxides. They act as acids when react with alkalis to give salt and water, and there is no reaction between acidic oxides and acids. However, there are some oxides that are both acidic and basic. They act as acids when reacts with alkalis, but also acts as bases when react with acids. They are amphoteric oxides. Metals oxides are ionic oxides with ionic bonding, and they are basic oxides. Sodium oxide and magnesium oxide are basic oxides because they can react with acids to give salt and water. However, they do not react with alkalis. The chemical equations for the reactions between each basic oxide and hydrochloric acid are shown here. The bonding in aluminum oxide is predominantly ionic with some covalent character, like 60% ionic but 40% covalent. It is because aluminum is more electronegative than sodium and magnesium. The electronegativity difference between aluminum and oxygen is lower than that between sodium and oxygen or magnesium and oxygen. Hence, aluminum oxide is both basic like ionic oxides and acidic like covalent oxides. It is an amphoteric oxide. It can neutralize both acids and alkalis. The chemical equations for the reactions between aluminum oxide and hydrochloric acid or sodium hydroxide are shown here. Note that when aluminum oxide reacts with sodium hydroxide solution to give a salt, but water is not produced. This is similar to the reaction between ammonia and hydrochloric acid. This reaction between aluminum oxide and sodium hydroxide solution is still classified as neutralization. The salt formed contains tetrahydroxoaluminate ion. Tetrahydroxoaluminate ion can be considered as 4 hydroxide ions attached to an aluminum ion. This explains why the charge of tetrahydroxoaluminate ion is -1. Non-metal oxides are covalent oxides with covalent bonding, and they are acidic oxides. Silicon dioxide, phosphorus pentoxide, sulfur dioxide, and dichlorin monoxide are acidic oxides because they can react with alkalis to give salt and water. However, they do not react with acids. The chemical equations for the reaction between each of the acidic oxide and sodium hydroxide are shown here. Note that all of these reactions are neutralization. You should be able to write these equations correctly. When we put the behavior of these oxides in water and the acid-base properties of the oxides side by side, we can see that they are closely related. If a basic oxide reacts with water, an alkali solution is formed. If an acidic oxide reacts with water, an acidic solution is formed. The solution only remains neutral when the oxides have no reaction with water, even though the oxide is acidic or basic. This also applies to oxides of other elements. Lithium oxide is ionic oxide, and so it is basic. Carbon dioxide and nitrogen dioxide are covalent oxides, and they are acidic oxides. You can pause to read this table. Again, there is no change in oxidation number of elements when the oxides reacts with water, acids, or alkalis. No redox reaction occurs. For example, the oxidation number of phosphorus is +5 in phosphorus pentoxide, phosphoric acid, and sodium phosphate. The oxidation number of magnesium is +2 in magnesium oxide, magnesium hydroxide, and magnesium chloride. This is true for all reactions introduced in this chapter.